Good morning, everyone. So today we'll continue with our calculus chapter, integral calculus, and now we're going to anti-differentiation, which is the inverse process to differentiation. So up to now, we described our functions y equals f of x, and we designed a process called differentiation. And with this process, we were able to calculate our derivatives, which we may express like this, dy dx or f prime of x. Now what we're going to do here is do the inverse, and that is the process that we call anti-differentiation, or simply integration. So this will be your integral. So let's take a look at one example. Let's say that I tell you that my derivative is x squared, and I ask you, what's the original function? So I should have some function f of x, which, well, y equals f of x, which I differentiate, and then I get x squared. So if we remember our differentiation process, if I differentiate x to the power of 3, I should get something with x squared, right? So when we have power functions, we drop the exponent 3 and we subtract it by 1. So we know that the derivative of x to the power 3 would be 3x squared. Now I may divide both sides here by a factor of 3. So if I do that, then I'll get to the derivative of x to the power 3 over 3 is x squared. So basically here I have found what is my function, that when I differentiate I get x squared. So here my antiderivative would be x to the power 3 over 3. So we have in a certain way done a anti-differentiation, and you can observe here that it's quite simple, and we can deduce some formula, some way to work with power functions. And let's see some more. So let's have a different function now. Our dy dx is x to the power 4. So again, what function can I get the derivative to get x to the power 4? Well, something to the power 5. If I take the derivative of x to the power 5, I would get 5x to the power 4, right? We drop the exponent x to the power 4. So I can divide both sides here by 5. And then I would have x to the power 5 over 5 is equal to x to the power 4. So do you see, this is our y here. So we have found that our function is y x to the power 5 over 5. So we can easily see that if our function is something like x to the power of n, when we anti-differentiate, this exponent will grow by 1, and that's exactly the same thing that we would have in our denominator here. So this is our anti-differentiation. And you can see that the inverse process works. If we differentiate, so if we get the derivative of this function, we would drop this exponent and subtract it by 1. So n, well, there's n plus 1 down here. So we would cross those out, and we would get back to x to the power of n. Now, what about the exponential function? So what if my derivative is the exponential function? Well, you should remember that the exponential function is quite simple. When we take the derivative of the exponential function, it's itself. Therefore, the integration will also be itself. So in this case, it's fairly simple. However, let's try and make this a bit more difficult. What if we had something multiplying here, x? So let's say dy dx is e to the power 2x. That's another example here. It's not the same one. So what would happen if my function was e to the power 2x? If I take the derivative, I would have, well, this would drop, right? Remember, in this case, you would take the derivative of this, right? Assuming that this is just a variable. So, because here we'll have to use the chain rule. We'll take the derivative of e to the power 2x, considering 2x as an unknown, so the derivative will be itself multiplied by the derivative of what's on top, which is simply 2. Derivative of 2x is 2. So the derivative of the whole thing would be e to the power 2x multiplied by 2. So if I want to get back to e to the power 2x, I'll have to divide both sides by 2. So we would then have this. And our y here was e to the power 2x. So take a look, when I get the derivative of e to the power 2x, I would have 2e to the power 2x. If I'm doing the differentiation, then I'll have to divide by 2, simple as that. So my function here, then, my anti-derivative, or my integral, would be e to the power 2x divided by 2. And there is some special way to formalize that. Usually, you're going to see in your books, in cognitive probably, the use of the capital F for the antiderivative. So let me show you. So we just discussed that dy dx equals to 2x means that y would be e to the power 2x over 2, right? So let's just label those things in a different way. So what if I just call this my function, right? This is my function now, and I'm not saying that this is a derivative of something. I'm trying to anti-differentiate this. So the symbol that we're going to use for anti-differentiation is simply f of x, but capital F. So if my function f of x is this, the anti-differentiation of it will be that. So same thing when we had, let's say, x squared. Now we know that the rule here, if we got the derivative, we would drop the 2 here to x to the power 1. But since we're doing the integration here, the anti-differentiation, then we're going to do the opposite. We're going to increase this by 1 and also divide by the exponent. So that would be x to the power 3 over 3. Now there's just one thing for you to notice, which sometimes seems odd to students, is that when you have a function in which you've got a constant, when you take the derivative, that constant vanishes. So, right, it vanishes because it's constant. So if you actually integrate this back, well, if you just assume that this was the only thing, you would get x squared. So this actually means that anytime you anti-differentiate a function, you're bound to have a constant. So you could have a family of functions with any c possible, and all of them, when you differentiate, you will get 2x. For example, if I had y equals x squared plus 2, the derivative would be the same. If I had x squared plus a million, the derivative would still be the same. So the antiderivative of 2x is in fact a family of functions. So that's why from the beginning we will only be discussing integrals which are defined. When we define our integrals, then we won't have to worry about this sort of stuff. So what if our function is, let's say, a mix of other functions? So let's say f of x is 6x squared plus 4x. So to get the anti-differentiation here, we can do it by parts. Just like when we were doing the differentiation, we can also do anti-differentiation by parts. So what is the antiderivative of 6x squared? Well, we already know that we increase our exponent by 1 and divide by the exponent, and let's multiply by this. Plus, now 4x, so x will increase to x squared and we'll divide by 2 and multiply by 4. That's our antiderivative. And if we go forward here, we would simplify this, 6 and 3, we get 2x to the power 3 plus, and here 4 and 2, we get 2x squared. Now if you're, let's say, unsure, if you're in doubt if this works, there are several ways for you to check it. First one is to take the derivative. What would be the derivative of this? And it should be equal to that, right? Let's see, 2x to the power 3, we drop the 3, so 2 times 3 times x, plus 2 times 2 x to the power 1. Oh, this is squared, this is to the power 1. So 2 times 3, 6x squared plus 4x. So we get the same thing, and it makes sense. That's only logical. Okay, let's see one more example now. So what about this case here? So I've got x to the power of a fraction. So, well, let's just do the same thing, right? So if this is our function f of x, this is a power function, isn't it? So we have, so far, we have seen that if our function is x to the power of n, the antiderivative of that function will be x to the power n plus 1 over n plus 1. So let's just apply that here. It might not be that easy to visualize as if it's a square or something like that. So let's just do this. So the antiderivative would be x to the power 5/2 plus 1 over 5/2 plus 1. Now what we have to do here is make it possible so we may work with those fractions. So we have to make the denominator the same. So 2, and to get 2 here, we'll have to multiply by 2, and same thing here, we'll have to multiply by 2. So 2 is the same on the denominator, and 5 plus 2, 7, over 5/2 plus 2/2, 7/2. Now we just adjust this so we have a nice number. There you go. That's our antiderivative. And if you take the derivative here, just to check, right, you're going to drop this exponent, 7/2 times 2 over 7 times x to the power of 7/2 minus 1. So 7, 7 to 2, this is 1. X to the power of 7 over 2 minus 1, let's divide by 2 and multiply by 2. So 7 over 2 minus 2 over 2, that's 5 over 2. And that's the same thing. Now, one important thing to notice that sometimes some of you might seem to forget is that this can be also written as a root, right? So x, this is the root, so it's a square root, and this is the exponent. So it's x to the power 5 and square root. So you may look at this function, you may be given this function in such a way, and you have to understand that it's that, right? Same way if the number was, let's say, 7 over 3, it's a cubic root. So you would have cubic root of x to the power 7. And I think that's enough for today. So next week, we'll begin with the fundamental theorem of calculus, and we'll be dealing with integrals and calculating areas with those. All right, have a great weekend, everyone, and you know where to find me if you have doubts. Just drop me an email.